Hey folks, welcome back. In this video we're going to look at free fall and terminal velocity. So let's get started. Now to demonstrate the ideas of free fall and terminal velocity, we're going to consider a certain scenario. So consider a skydiver jumping out of a plane. It says that they start to accelerate towards the ground due to the influence of gravity alone, i.e. their weight. We say that they are in free fall. So any object that is under the influence of gravity alone, we say to be in free fall. As they accelerate downwards, the air resistance, i.e. the drag upwards, will increase. Eventually, the forces acting vertically on the skydiver become balanced, i.e. their weight will equal their drag, and they fall at a constant speed. This speed is called the terminal velocity. So if you look at this diagram here, we can hopefully make sense of this. So as soon as the skydiver jumps out of the plane, they are said to be in free fall, so they are experiencing a weight downwards. However, as they fall, they're going to increase in speed downwards, and that means that they're going to experience a greater air resistance moving up the way. And that drag or air resistance force up the way will increase until the drag upwards balances the weight downwards. And that means that because we've got balanced forces at this point, the skydiver is going to travel with a constant velocity or a constant speed, and this is called the terminal velocity. Now the first terminal velocity reached from a skydiver is going to be too fast to hit the ground at, so it's not safe to hit the ground at that kind of speed. So what they need to do is open the parachute. Now when the parachute is opened, it says that again the air resistance or drag upwards increases, so the speed decreases. So we know that opening the parachute will cause a greater air resistance upwards, and that's going to slow the skydiver down. It then says a lower terminal velocity is eventually reached when the vertical forces again become balanced. Now looking back at the picture, it's important to see that weight is going to always stay the same, because remember that's just defined by the mass of the skydiver times by the gravitational field strength. So if the mass of the skydiver stays the same, and so does the value of gravitational field strength on the earth, then the weight is going to stay the same. So that's why that size of force vector doesn't change. But it's the drag or air resistance force that does change. Now I'm just going to show you a quick simulation to help you understand this. So if we look here, we've got a plane with a skydiver inside, and if I click play, they jump out. And remember we said that at this point they're going to be in free fall, so they're experiencing the force of gravity alone, i.e. their weight. However, eventually the drag force is going to increase as they increase in speed, and the weight stays the same downwards, and that's because at this point the weight is greater than the air resistance. So they're going to increase in speed until eventually the forces become balanced, so we say that at this point the air resistance equals the weight, so the speed is constant. And remember the skydiver is said to be at terminal velocity at this point. If we look back at the notes, we've now got a velocity time graph for the free falling skydiver. So we've got velocity on the y-axis against time on the x-axis, and you'll see it goes up to 60 seconds. And we've also got speeds of up to 60 meters per second as well. And if we break this down into parts, you'll be able to understand what's going on at each stage. So remember we said that a positively sloping line on a velocity time graph represents an acceleration. Well, this is where the skydiver is free falling through the air and they're accelerating. But eventually that acceleration is going to decrease as the air resistance upwards increases. So we've got this curve to show that increase in the air resistance there. And then eventually the velocity becomes constant. And this is our first terminal velocity, i.e. constant speed or constant velocity. But then after a while of traveling at this terminal velocity, the skydiver is going to open their parachute, at which point we're going to get a massive increase in air resistance, and this is going to rapidly slow down the skydiver. So we're going to get this rapid deceleration, this decrease in velocity shown here, until eventually the drag upwards balances the weight downwards again, at which point we get a second terminal velocity, i.e. constant speed shown here. So it's worth being able to explain what's happening at each stage on the velocity time graph for a free falling skydiver. Lastly, I'll just show you a quick simulation to help you visualize this. So if you have a look here, we've got a skydiver that's actually in a hot air balloon this time, and we've also got a velocity time graph shown here. So we're going to see how the velocity time graph is traced out as we look at the motion of the skydiver. So I'll just click play to show you all the way through, and then we'll break it down into parts. So let's start that again and look at each stage in turn. So if we click play, we've got free fall, so we've got this acceleration. However, remember we said that as the air resistance force increases upwards, we're going to start getting this curving off of the velocity. So we'll keep playing that there until eventually the two forces become balanced and we get this constant velocity, the first terminal velocity. We're then going to open the parachute, and you'll see we've got this massive decrease in velocity, this rapid decrease from the massive air resistance upwards. But then eventually that will decrease to balance the weight again, where we get the second terminal velocity as shown here. And then when the skydiver reaches the ground, we get another little decrease in velocity there. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.